Hello, algebra students, and welcome to your lesson on systems of linear equations and their solutions. This is going to be our last lesson where we're talking about systems of equations, and in this lesson, we're going to be looking at this objective here, which says, let's find out how many solutions a system of equations could have. As our warm-up question, we've got this activity here. It says Olalekan is trying to solve this system of equations. And they give us the system x plus y equals 3 and 4x equals 12 minus 4y. It says, looking at that first equation, the x plus y equals 3, he thought the solution to the system is a pair of numbers that adds up to 3. That seems right. We've got x plus y. Those are our two variables, and that equals 3. So it means it must be a pair of numbers that add up to 3. And he says, I wonder which two numbers they are. In a moment, you're going to go ahead and pause the video and look at numbers 1 and 2. Number 1 says choose any two numbers that add up to 3. Let the first one be the x value and the second one be the y value. And then once you've chosen your pair of numbers, the pair of values you chose is a solution to the first equation because it's a pair of numbers that add up to 3. Check to see if it is also a solution to that second equation. And then you'll pause for a brief discussion with your group. So go ahead, pause the video now and try questions 1 and 2. All right. Well, number 1 just tells us we need to pick any two numbers that add up to 3. And so depending on who's reading that, there's a lot of different possible pairs of numbers that add up to 3. Maybe you were thinking of the pair of numbers 0 and 3. I'm going to use that pair of numbers. Let's make 0 my x and 3 my y. It tells us based on that pair of numbers we pick, check to see if this pair of numbers is also a solution to that second equation. Well, for me to check to see if it's a solution to the second equation, I need to substitute both of those numbers into the second equation. When I do that, I get 4 times 0 equals 12 minus 4 times 3. When we do the math, we get 0 equals 12 minus 12, which is true. So that tells me that pair of numbers 0 and 3 is a solution to the first equation and a solution to the second equation. So it's a solution to the system. Now, like I said, depending on who's watching this, you might have picked a different pair of numbers than I did. Let's do one other example. Let's say you didn't pick 0 and 3. Let's say you picked 1.5 and 1.5. That's also a pair of numbers that adds up to 3. Well, if I were to check 1.5 and 1.5 in that second equation, we would get 4 times 1.5 equals 12 minus 4 times 1.5. 4 times 1.5 is 6. So we get 6 equals 12 minus 6, which is also true. So what's that telling me? Well, it's telling me 1.5 and 1.5, that combination of numbers, is also a solution to the first equation and the second equation. And depending on what pair of numbers you picked at home, you might have gotten another combination of numbers that's also a solution. Whichever pair of numbers you chose, if they added up to 3 for that first equation, you should have also found that they were a solution to the second equation. So what does this mean? Well, let's go on to number 3. Number 3 is asking, how many solutions does the system have? Use what you know about equations or about solving systems to show that you are right. Based on our observations from number 1 and 2, you might already have an idea what the answer is to this question in number 3 that asks how many solutions does the system have. Before we answer that question, I want to think of this question or the system in one other way. Let's go ahead and solve it. We haven't solved the system yet. In past lessons, we've talked about different ways you can solve. One of the ways we talked about with solving algebraically could be using substitution or elimination. I'm going to go ahead. I'm going to choose substitution because I see that first equation, x plus y equals 3, and I know I can rearrange that to solve for a specific variable to help me substitute. I could take that equation, x plus y equals 3, and if I were to subtract y on both sides, that would get me x all by itself, and then I could substitute x. I encourage you to go ahead, pause the video now, and finish solving this system. See what happens and what you get as your result. Well, if I substitute x equals 3 minus y into that second equation, it's going to say 4 times 3 minus y equals 12 minus 4y. I have to distribute that 4, so that gives me 12 minus 4y equals 12 minus 4y. And, that's weird. I've got the same thing on both sides. If I were to bring y to one side, let's do that. If I were to add 4y on both sides, I'm left with 12 equals 12. Notice I'm not getting a solution. I'm not getting x equals a number or y equals a number like we're used to seeing when we solve systems. Well, let me try one last thing. We had talked about different methods you can use to solve a system of equations. So solving algebraically is just one, but I don't seem to be getting a solution here. Let me try solving by graphing. We had said if you were to graph both of these equations, that solution point should be that intersection point. So let's do that. I'm going to switch over to our graphing calculator. That first equation is x plus y equals 3. I'm going to have to peek at what that second one is. 4x equals 12 minus 4y. 4x equals 12 minus 4y. What do you notice there? Well, there's our first line. Here's our second line. They're the same line. They're the same equation. We've got two lines that are on top of each other. Now, we said when we're solving by graphing, we're looking for that intersection point. That intersection point is going to tell me that combination of numbers that's a solution for both of the equations. But my equations are the same. Where are these lines intersecting? They're intersecting everywhere because those lines are on top of each other. That means any point on one line is going to be on the other line, and any point that's a solution to one equation is going to be a solution to the other equation. If I zoom in, remember I had picked 0, 3. Well, 0, 3 is on that line. I had also picked 1.5 and 1.5. 1.5, 1.5 is right there. It's also on that line. And any combination you might have picked, maybe you picked 1 and 2, that combination is on this line. There's going to be a lot of different combinations of numbers that are solutions to this. So if we come back to the question, how many solutions did the system have? Well, you might have already been able to tell from earlier when we were guessing pairs of numbers, it's got a lot of solutions. One solution is the combination 0, 3. Another solution is the combination 1.5 and 1.5. You might have picked 2 and 1. You might have picked negative 1 and 4 because it could also be a negative number. There are many, many solutions. When this happens with a system, we say that system has infinitely many solutions. The system has infinitely many solutions. And there's a couple different ways you can come to that conclusion. One is just making the observation that for any pair or any pair of numbers, any solution for the first equation is also a solution to the second equation. That's what we were doing in 1 and 2. Another way you can get to that conclusion is when you're actually going to solve. When I went to solve algebraically, notice my variables canceled out. They eliminated, and I was left with this right here. I was left with 12 equals 12. If you're left with a statement that's true, like 12 equals 12, 100 equals 100, 5 equals 5, if all those variables eliminate and you're left with something that's true like that, that tells us there's infinitely many solutions. And then the last way is what we were doing here. If I went to graph that system and I see those lines are the same, that is also telling me that there's infinitely many solutions because there's infinitely many points where those two lines intersect. If I pick a point on one line, it's going to be on the other line because they're in the same place. So when we talk about our objective up here, which is how many solutions a system has, all of the systems we've been looking at before today had one solution. There was one pair of numbers for x and y that satisfied both of the equations. That's not always going to be the case. Another option is what we're seeing here, where there's infinitely many solutions. Before I leave this question here, I want to come back and look at these two equations again and compare the structure of the equations. Another way you can come to this conclusion that there's infinitely many solutions is by seeing that these equations are equivalent equations. We noticed that when we went to go graph that these equations are the same. There's a way to look at the structure of the equation itself, not a graph, but look at the equations and see, yeah, those are equivalent equations. I'm going to come down here to where I originally, when I was going and using substitution, notice I solved for x here. I got x equals 3 minus y. I'm going to come back up here and write that down. We got x equals 3 minus y. When I'm comparing that first equation, x equals 3 minus y, to this second equation here, I notice something. Think back to when we were talking about equivalent equations. How could I reason that these two equations here are equivalent equations? Well, I noticed that if I were to multiply both sides of my equation by 4, notice it would give me that second equation there. If I were to multiply x by 4, I get that 4x. And if I were to multiply 3 minus y, that entire thing by 4, I get 12 minus 4y. Finding equivalent equations, you can do that by multiplying a constant like 4 on both sides of the equation. So when I mentioned earlier, another way you can identify that this system has infinitely many solutions is by looking at the structure of the equations. If you noticed early on that these are equivalent equations, knowing that they're equivalent equations also tells you there's infinitely many solutions. Because they're equivalent equations, that means if something's a solution to one equation, it must be a solution to the other equation. We're going to continue to do what we were doing here and look at the structure of these equations as we move through the remainder of this lesson, so be on the lookout for that. We're going to come down to the next part of our lesson here to give us another example of a system of linear equations, and we'll talk about what the solution is. For this next one here, the activity is called What's the Deal? And it tells us a recreation center is offering special prices on its pool passes and gym memberships for the summer. On the first day of the offering, a family paid $96 for 4 pool passes and 2 gym memberships. Later that day, an individual bought a pool pass for herself, a pool pass for her friend, and 1 gym membership. She paid $72. The first part of this question asks us to write a system of equations that represents the relationships between pool passes, gym memberships, and the costs. Be sure to state what each variable represents. Notice it's asking us to write a system of equations. Right away, that's a clue that you should be writing 2 equations. It also tells us make sure you are defining your variables and what your variables represent. I'm going to have you go ahead, pause the video, and see if you can come up with a system of equations that represents this scenario here. All right, when we go to write our system of equations, that first equation is going to come from that family purchase. It tells me they order 4 pool passes and 2 gym memberships and pay a total of $96. So I get that equation there. X for me is going to represent the cost of a pool, not a pool pass. And my Y is going to represent the cost of a gym membership. If you just wrote pool pass and gym membership, I'm going to push you, try to make these variables, your description, as specific as possible. I could tweak the wording of this problem. Instead of knowing the cost, we might not know how many they purchased. So you want to make sure you're specific. You don't just say pool pass, but we're going to say the cost of a pool pass. We're multiplying how many pool passes the family bought by the cost. We're multiplying how many gym memberships they bought by the cost. And together, that's going to give us the total cost they paid, which was the $96. Similarly to that, the individual here is going to be our second equation. They bought a pool pass for themselves and for a friend, so that's 2 pool passes. 1 gym membership. You could write 1Y or Y by itself. and they paid a total of $72. So that's our second equation in our system. So together, this pair of equations here represents this system of equations, and this system of equations here represents this relationship described in this story. In number 2, it tells us to find the price of a pool pass and the price of a gym membership by solving the system algebraically. Explain or show your reasoning. We've talked through in our past couple lessons how you can solve systems of equations. They're naming solving it algebraically. So the strategies we learned to solve algebraically are substitution or elimination. I'm going to have you go ahead, pause the video now, and solve this system here algebraically. All right. When I'm looking at this system here, my mind, because I notice that the x's and the y's are on the same side of the equation stacked up like that, my mind goes straight to elimination. Both of these equations are in standard form, which it can be really helpful when you're solving by elimination. If you could have also solved by substitution as well, but you would have had to rearrange one of those equations to solve specifically for a variable so that it says x equals or y equals, and then use substitution, which you can do. And if you chose to do that, that's awesome. I'm going to solve using elimination. I've got my 4x plus 2y equals 96. To get something to eliminate, let's get x to eliminate. And for x to eliminate, I'm going to need to change that 2x to a 4x so that they're the same and I can subtract. It means I need to multiply that second equation by 2. So let me do that. If I do that, that gives me 4x plus 2y equals 144. That top equation's still the same. So it's still 4x plus 2y equals 96. Now that I've got both of them being 4x, I can come in here and I can subtract. I'm going to subtract that second equation from the first equation. Now when I do that, I get 4x minus 4x. That cancels out or eliminates. That's what I was trying to do. But when I keep going through, I've got 2y minus 2y. That also eliminates. I've got nothing left over here on that left side of the equation. There's nothing left, so that means it's just a 0. And then over here, goodness, 96 minus 144. Is that negative 48? Yes, it is. So we're left with no variables because both of my variables eliminated. I'm just left with 0 equals negative 48. Okay. Well, before we come to any conclusions, I want us to do one more thing. Number 3 tells us to use graphing technology to graph this system of equations. Right away, I'm seeing I've got this. They wanted me to solve for what x and y is, but this isn't getting me closer. But maybe I can use a graph to help me determine what our solution is. Just like we said earlier, if we're solving by graphing, that solution point should be where those two lines intersect. I want to see if I can copy and paste this in. Could I be so lucky? I can be so lucky. So I got one of my equations, and here's my second equation, and I'm going to have to back out. All right, what do we got? Well, we said a moment ago that when you're solving by graphing, I'm looking for that intersection point. What do you all think here? Well, I'm looking at these two lines. These two lines are not intersecting. They are not crossing each other anywhere. The word we could use for these two lines is they are parallel lines. Parallel lines are lines that go the same direction, and more importantly here, never cross. These lines are not going to intersect. So let's come back to our problem here. I've got, when I graphed those two lines, I saw that the lines are parallel, and don't intersect. When I solved algebraically, well, I couldn't solve because both my variables eliminated, and I got something like this. Now, this is similar to what happened earlier. Remember earlier when we went to go solve, I got 12 equals 12. We got something that was true, and therefore we said there were infinitely many solutions. Down here, I'm having both of my variables eliminate, and I'm getting something that's not true. 0 does not equal negative 48. When I look at our system, I also see those two lines aren't intersecting anywhere. All of these things are telling us that there is no solution to this system of equations. As soon as you see those two lines don't intersect, there's no intersection point. It means there's no solution point. Algebraically, what that looks like is something like this line here. It looks like you solving the system, but having both of those variables cancel out or eliminate and being left with something that's not true, like 0 equals negative 48. Both of those things are telling us there's no solution to this system here. Now let's come back up. What does that mean in terms of this scenario here, the story? What does it mean that there's no solution? Well, our solution, remember, we were trying to find the cost of a pool pass and the cost of a gym membership in these two purchases. When we got that there's no solution, it means there's no combination of pool pass cost and gym membership cost that would make both of these equations true. It means that these two groups paid different amounts. They told us at the beginning they're offering a special price. Well, maybe that special price only applied for families and not like if you're purchasing as an individual. But it means that that unit cost of a pool pass and of a gym membership was different for each of these two groups here. We can see that down here when we doubled the amount that individual ordered. If the family ordered double the amount, notice they ordered double the amount of pool passes, double the amount of gym memberships. If they were paying the same price, the individual and the family, we should see that cost is doubled. But we see that that's not the case here. When I doubled that second equation so that they had the same amount of pool passes, the same gym memberships, I see that those total costs are different. So right there, that's a red flag that they weren't paying the same price for the pool passes and the gym membership. That's also getting into what we had been talking about earlier and making these conclusions based on the structure of the equations. In this step here, I'm making the structure on that left side the same, but I'm noticing that there's no way that 4x plus 2y equals 96 in one scenario and 144 in another. There's no value for x and y that could make it simultaneously equal 96 and equal 144. Hence, the no solution. The last thing you could do is you could change these equations into slope-intercept form and make an observation from that. So let's do that. When I take the second equation here, I'm going to start with that one because it's already pretty close to slope-intercept form. When I take this equation and solve for y, we would do that by subtracting 2x on both sides, and you get negative 2x plus 72. If I take that first equation, if I want to change it into slope-intercept form and solve for y, we would have to start off by subtracting 4x on both sides. That leaves us with 2y equals negative 4x plus 96. And then our last step, we've got to divide both sides by 2. When I divide both sides by 2, I get y equals negative 2x plus 48. Comparing these two equations here, now that they're both in slope-intercept form. Remember, you change things into slope-intercept form so that you can observe those two things. You can observe slope and intercept. Looking at these two equations here, I see that the two equations have different intercepts. They have different y-intercepts, which if I switch back to our equations here, notice they have different y-intercepts, but the slope is the same. The slopes for both of them are negative 2. When it comes to parallel lines go the same direction. Well, slope tells you the direction of the line, so if the lines are parallel, they'll have the same slope. So this last way you can identify if a system has no solution, is this idea that a system has no solution if those lines are parallel and don't intersect. When it comes to the structure of the equations, that would mean both of those equations have the same slope. This next part here is a great opportunity for us to practice all of these observations we've been making specifically around structure. This activity here says sort these systems into 3 groups based on the number of solutions each system has. Be prepared to explain how you know where each system belongs. So we've got these systems here that we're going to be sorting into systems that have one solution, systems that have no solution, and systems that have many solutions. Now, one way you can do this is you can solve, just like we've been doing. You can solve algebraically using elimination or substitution, or you can solve graphically. I want to use this activity here, though, as an opportunity to practice what we've been talking about in this lesson with structure. Namely, this idea that if we come back up here, that systems that have infinitely many solutions have infinitely many solutions because those equations are equivalent equations. And systems that have no solution because those equations are parallel lines, meaning they have the same slope and different y-intercepts. Without solving systems, if you can make those observations, that can tell you how many solutions they have. So for example, looking at A, I want to compare the structure of these equations. There are many ways you can go about doing that, but one way is I notice this equation right here is really close to being in slope-intercept form. All I would have to do to get y by itself is divide both sides of the equation by 3. So I'm going to go ahead and do that. When I divide both sides of the equation by 3, we get y equals negative 9 divided by 3 is negative 3. And negative x divided by 3 is negative x over 3. Or if you're thinking of that number in front of x as a 1, 1 divided by 3 is 1/3. So we get negative 1/3 x. Now that I've rearranged that second equation in slope-intercept form, I can compare these two equations here and see that, well, look, they're the same equation. I've got negative 1/3 x and negative 1/3 x, and I've got negative 3 and negative 3. Just by doing that one small change to that second equation, I was able to compare the structures of the equation and see that they are, in fact, equivalent equations. You could have gotten to that same result by multiplying that first equation by 3 and seeing that it's the same as the second equation. Because we've identified that these are equivalent equations, I don't have to solve anything. Because I've identified their equivalent equations, what does that tell me about the number of solutions? Where should that system go? Well, they're equivalent equations. That means if something's a solution for one of the equations, it's got to be a solution for the other equation. That would mean that system A here has many solutions. Let's do one more example together and look at system B. So in system B, I want to compare the structure of these two equations. So let's see. Let me see if I can make the second equation look more like this first equation. First thing I notice is this first equation just has x all by itself. So if I wanted to get rid of that 5, that would require me to divide by 5. So let me go in and do that. Let me divide both sides of the equation by 5. When I do that, that gives me x equals 4y plus 60 divided by 5 is 12. So we get my second equation looks like that. They're looking more similar now. But I noticed that that first equation has x and y on on the same side. So let me do that. Let me change that equation, and I can bring that 4y over to the left side by subtracting 4y. So let me do that. I would say x minus 4y equals 12. So by doing those two moves, I've changed that second equation to look like this now. So now I can compare those two equations. Well, what do we think about this? Well, unlike this first system here, these are not the same equation. We've got that original first equation, x minus 4y equals negative 12, and I've changed that second equation to look like x minus 4y equals 12. Well, since they're not the same equation, it means they don't have infinitely many solutions. It means they're not equivalent equations. Think through it more. Do we think it has one solution or no solution? Well, any pair of numbers you pick for that first equation, where that left side equals 12, notice for that second equation, it also has x minus 4y, but in that second equation, it says equals negative 12. If it's a solution for this first equation and equals 12, it can't also equal negative 12. So by changing that second equation so that that left side of the equation looks the same, but seeing that on the right side, one of them says 12 and the other one says negative 12, there's no way for it to be a solution to that system. You don't believe me? Pick a pair of numbers that could be a solution to one. It's not going to end up being a solution to the other. For example, if we let's pick x equals 16 and y equals 1. I chose that pair of numbers because if x is 16, y is 1, it equals 12. But notice if I do that same exact math, if I put 16 here and 1 here, it still is going to equal 12. It's not going to equal negative 12 for that second time. So we've got the solution B here is going to have no solution. I did those first two as examples. Go ahead, pause the video now, see if you can sort the remaining 4 equations. All right, real quickly, as you are sorting them, system C here, those equations are not equivalent. They have different slopes, which means they would intersect and have one solution. System D here, I see that those slopes are the same. That means they're going to be parallel lines. They have different y-intercepts and the same slope. Parallel lines never intersect, which means they have no solution. These two equations here are already in slope-intercept form, which makes it easy for me to see that they have different slopes. That tells me that they are going to be intersecting and have one solution. And then for this last one here, you might have to do a little rearranging. My strategy would probably be, I noticed that this second equation here, I could divide everything by 4. That helps because it gets x all by itself. So we get x minus 4y equals negative 4. If I wanted x all by itself like it was in that first equation, I would have to add 4y on both sides. And when I do that, we get, hey, look, the same as the first equation. That's showing me that they're equivalent equations. And if they're equivalent equations, that must mean that they have infinitely many solutions. Because if it's a solution to the first equation, it'll be a solution to the second equation because they're equivalent. The last part of this lesson here is going to help us summarize all the stuff we've been looking at in this nice handy table here. We've seen in this lesson that there are 3 possibilities for the number of solutions a system can have. It can have one solution, like all of the systems we've looked at prior to this lesson, but it could also have many solutions or no solution. There's 3 things for us to summarize here. The first is the equations, specifically what the equations look like. Think about all the comments we've been making on the structure of the equations. The second one is the graph. We've graphed a system that has each of these number of solutions. So think through like what that graph looks like. And then this last one, the solutions themselves. So if you're solving that system algebraically, what does it look like when you're solving? What's that end result look like? I encourage you to go ahead, pause the video now, see how much of this you can fill out on your own, and then come back to do that final summary together. Alrighty. So in these, let's start with the equations here. If it has, I'm going to come down to many solutions first. Many solutions, the theme of today is that they are equivalent equations. Equivalent equations meaning that I can change one equation to look like the other. An example could be something like y equals 3x plus 2. And if I were to double that equation 2y equals 6x plus 4. Those are equivalent equations. No solution, we said, are going to be parallel lines, meaning they have the same slope and different y-intercepts. They aren't completely equivalent, just the slopes are the same. So if I picked a similar equation to that first one here, y equals 3x plus 2, remember your slope is that 3 right there with the 3x. So that second equation would have to have the same slope, but a different y-intercept. So maybe a -2 instead of a +2. One solution would be anything else. It would be equations that aren't equivalent and equations that don't have the same slope. So, for example, if we had 3x plus 2, if that second equation had any different slope that wasn't 3, so I don't know, 4, 4x plus 2. Those two lines there have different slopes. It means they would be intersecting in a single point, which takes us nicely to this next column here on the graphs. When you are talking about a graph of a system, I'm going to use my straight line here. If it has one solution, that's what we've looked at prior to today. That would be any two equations there that are intersecting at that single point. We saw that systems with many solutions are equivalent equations, and what that looks like when you go to graph is you've got one line and then the second line is right on top of it. No solution, we've already mentioned, are parallel lines. Parallel lines are lines that are going the same direction, and because they're going the same direction, they don't intersect. These are all examples. Obviously, those parallel lines could go a different direction. That intersection point could be somewhere different. Those two lines there could be going a different direction. But the idea is, for the graphs, one solution is going to have one intersection point. Infinitely many solutions are the same line, meaning there's infinitely many intersection points. And no solution are parallel lines, and so there's no intersection point. For this last part here, the solution, so when you actually go to solve, what does it look like? Well, for this first one, it looks like you getting a solution. If you were to solve, you've got x equals a number and y equals a number. It looks like if you're solving algebraically, you are actually able to isolate the variable. You're able to get x equal to a number and y equal to a number. If you're solving algebraically a system with many solutions, I'm going to take us back up. So that very first one we did here, it looks like this. It looks like those variables both canceling out and just getting left with a statement that's true, like 12 equals 12. So we could write that for our example down here. Our example could be 12 equals 12. And just a note to put with it, maybe both variables cancel or eliminate, and we are left with a true statement, like 12 equals 12. No solution is the opposite. So no solution is both variables cancel or eliminate, but we're left with a false statement. So that could be something like, I think earlier it was 0 equals -48. 0 does not equal -48. That is not true. So if we were solving algebraically, that's what no solution would look like. I think this table is a really great summary of everything we discussed in this lesson. So if there was anything you were taking notes on in this lesson, it better be this. This table here will come and will be very handy when it comes to completing future questions on systems. That is also where we stop today. Thank you so much for watching, and have a wonderful rest of your day. Bye.